Hi guys, it's a great honor to join the BES conference this year, and my name is Haoran, a DPhil student at the School of Geography and Environment at the University of Oxford. Also a DPhil student in the Liverpool Centre for Nature Recovery at the University of Oxford. I'm funded by the Scottish Forest Trust, doing my DPhil research. So today I'm going to show you my master's work in the past 2 years, which is looking at the ecological impact of the global forest pests and diseases. So, as a forest ecologist, I have been engaged with the forest for more than 5 years. During my undergraduate, I work in the Chinese forest and figure out a lot of pine trees injected by the pesticides to avoid the plant pine well disease. And also happening in the Europe is the ash dieback disease, which devastating the European forest health, the vulnerable ash trees. And you can see the photo taken in the Wyden Woods, which is a typical British woodland, and the Oxford Ecological Laboratory, and you can see the crones are removed by the fungus. So actually that's the invasive pests and diseases happening globally from the North America to Asia to Europe, and we have so little information about what it is going to be, the effects of them to the global forest health in the future compared to the wildfire and droughts. So, but actually the pathogens are a serious issue because you can see from the 2023 survey, you can see the emerging infectious tree diseases doubling every decade, which is a very big amount. And it really causes a great ecological impact ranging from the carbon sequestration loss and the biodiversity loss and the big cost for the society. And research by the University of Oxford estimates that the ash dieback disease has cost about £15 billion to the society. But unfortunately, these are neglected by the global nature policies like the global carbon budget, which mentions the effect of the wildfires to the carbon credits, the land carbon stock, but does not really count the effect of a pathogen and disease, which might remove a lot of tree crones, leaving the dead stems standing on the forest, but without any photosynthesis, which is problematic. And also policies like international carbon credits also mentions kind of environmental risks without assessing the impacts of the forest pathogens and disease, which can be kind of problematic. So we really need to know how the pathogens is affecting our trees in the future, and how to what extent this is going to affect our future. But the challenging thing is that there's a complexity of the interaction between host pathogens and the environment. So as the human activities change, as the climate change, these interactions are changing over time, and the disease outcome can be altered by many pathways, like the changing temperature and changing precipitation patterns is going to affect the host by kind of stressors like droughts and flooding and heat wave. These are able to attack the trees and make the trees vulnerable to the disease. This positively affected disease severity. And also, global climate warming and increasing precipitation can increase the reproduction of pathogens and insects, which make the disease even worse. So how are we going to separate these effects is very challenging, and we can't make the controlled experiment to separate these effects. And fortunately, there's some kind of complexity science as a separate field and a forecasting tool. Fortunately, this tool has been proved to be effective to make environmental policies and social science policies, and also so they are recently used by several ecologists. And I've written a paper with my master's course mates to demonstrate how the complexity science what's the implication of complexity science to nature recovery and biodiversity conservation. So the complexity of the ecosystem includes a variety of species interactions with environmental variables in a desired state, because nature recovery is often we want to recover the nature to a desired state from the degraded environment to ensure the system's stability and resilience. And the complexity science, the strength of the complexity science is that we have a range of tools from qualitative mapping to quantitative modeling. Some of you guys may heard about qualitative mapping, like the rich picture, the causal loop diagrams, and also for the quantitative modelings, like the individual-based modeling, the differential equations, and so on. So these allowed us to choose a different kinds of methods, and like the systematic mapping, systematic review, evidence-based conservation, and causal loop diagrams and individual-based modeling. We have a range of tools to understand what are the interactions reside in the system, and how we're going to understand the system dynamics using a diverse of scientific tools. And using these tools, I'm able to forecast the impacts of the ash dieback disease to the forest health in the future. So my master's work is mainly assessing how the ash dieback disease is gonna affecting the European forest health. And my first paper was looking at whether the planting resistant trees is gonna to save the ash population. And I use the Wyden woods as an example for establishing my model. And we had an NERC-funded research to establish an ecological plot in 2019 to collect the disease data, to record the disease incidence and the chrome conditions in the Wyden woods. And I also conduct a systematic review to gain insight from 386 papers, which allows me to study the cause and effects in the ash dieback system. So I'm able to draw and causal loop diagrams of the ash tree, pathogen, and environment. And what I do is to select the most important elements and interactions in the system to justify why I choose certain quantitative variables in a model and why this topology of the quantitative model. And these allow me, this acts as a model principle or guidance for quantitative modeling. And with the quantitative model, I'm able to forecast how many trees are going to be removed by the disease over the 10-year and 15-year time course. So the society is interested in to what extent is planting resistant ash trees is effective to buffer against ash dieback. And my model suggests that if we maintain a very small proportion, perhaps around 15% resistant ash, this can maximize nature selection power to outweigh the susceptible ash and maintain the resistant genotypes. And also my model suggests that if we increase a 5% of resistant ash in the woodlands, we can save more 3% ash. So this conveys a positive message that we don't need a big amount of resistant trees. We only need to maintain a small proportion, like 50% of them, to make effective nature recovery strategies in the diseased ash woodlands. And what about the climate change on the ash dieback disease? My second master paper giving a positive answer to this question, which is climate change has limited impact on the ash dieback fungus virulence. This is based on a systematic review from over 3,000 papers, and I collected data from 80 peer-reviewed disease census across the Europe and over 1,000 mortality data across the Europe. So what I found is that if we assume a 1.5 global warming, we only observed less than 2% of annual mortality rates of the ash trees. And if we assume 1% millimeters precipitation change, we only see less than 1% annual mortality rate change of the ash trees, which is very little, and can be offset by planting resistant trees. So it really conveys a positive message, like planting a small amount of resistant trees can save ash from being aggravated by the effect of the climate change. Looking at the future, which is the DPhil program, my DPhil program starts this year and will be ended in 2026. My DPhil program will be compiling the global tree pest disease database with the help of the natural language processing or the AI. So during my master's, I was looking at ash dieback disease and compile a global database from the 880 population census papers, and these will be used as a training data for trained language models that will be used in doing my DPhil, scaling up my research to a variety of different tree pests and pathogens, and the trained language models will be used for a machine screening to identify which paper has the population census data and which paper don't have. This increased the efficiency for me to analysis to compile a bigger data from a huge range of literature pools. So that covers the main content of my research, and I'd like to thank my master supervisor, Dr. Cecilia Dashu, and Professor Yadavinder Mali for your guidance at the University of Oxford, and they are also my DPhil supervisor in the next 2 years. Thank you very much for the Scottish Forest Trust for funding my DPhil research, and thank you all, the Livingston Centre for Nature Recovery, the Oxford Biodiversity Network, and my master's program, Biodiversity Conservation and Management at the University of Oxford, for getting me a very amazing international and interdisciplinary community for sharing and exchanging ideas on different aspects of the conservation. These are incredible opportunity for me to gain knowledge on the nature restoration, conservation, and the nature-based solutions stuff. And thank you all for listening to my master's work. Thank you.